little bit tricky, which is matrix representations of linear transformations on vector spaces. Matrix representations of linear transformations. Be really important to understand is the map. So just to recall, if you have a vector space, V a vector space, and B a basis, right? So you have an n-dimensional. You have some n-dimensional vector space, and you have a basis. Right? Then we have a map from the space to Rn. Right? Then we have a map from V to Rn. Right? Namely, the map that goes from takes a vector and then gives you the coordinate vector of V with respect to that basis. So I hope you all remember how this goes, right? You start off with right. You start off with a vector, and then you look at the unique linear combination of the B's of the BI's that gives you that V, and you take the coefficients, and those coefficients make the coordinate vector, right? Right. So right, how does this? What is B? What is B? What is the coordinate vector with respect to B? Right, it's you take one expresses B as Ci C1 B1 plus Cn Bn, right? And then the coordinate vector with respect to B is just the vector of those coefficients. And we commented last time that this map is an isomorphism, right? It's a linear map. It's 1-to-1, and it's onto. This map is an isomorphism. Okay, and we have, as an isomorphism, we have a reverse map, right? Going from Rn back to V, if you start with some coordinates, right? Somebody gives you some coordinates, you know. What does the reverse map look like? So the inverse map. The inverse transformation, right? Goes from Rn back to V, right? And you start off with, you know, some numbers, C1 through Cn, and you return to a vector, C1 V1 plus Cn Dn. And clearly this map reverses what the coordinate map does. Right? This map, the coordinate map goes from the vector to a bunch of coordinates, right? And this thing goes from some coordinates back to a vector, vector. Okay. So everyone okay with that? That's crucial. If you have questions about this, please ask them right now. Okay. So So I'm gonna erase this. Is that okay? Anyone copying? No. Okay. So here is the statement of the theorem that will give us the matrix representations. Okay. So the V and W, now they wrote it like this. You've got T from V to W, a linear transformation. Right? So a linear transformation between vector spaces. Okay? And you have some bases. So E is V1 to Vn, and F is from W1 to Wm, right? So V is some n-dimensional space, and W is m-dimensional. So V is n-dimensional, W is m-dimensional. Yeah, Mia.
And E and F are bases?
E and F are bases. So I guess previously I've always used cursive letters to denote the bases. So maybe it's, right, like I've always used some sort of fancy looking B, right? So maybe it's more, it helps you remember that these are the names of bases if I write them in cursive letters. Okay. So the claim is that there exists a matrix A going from R, a matrix A that's an n by n matrix that such that for all V and B, A times the coordinate vector of V with respect to the E basis equals the coordinate vector with respect to the F basis of TV. Okay, and this matrix is considered to represent the linear transformation. Right? It basically encapsulates exactly the behavior of the linear transformation. Okay. So it's like this, right? You got V, W. Here's the picture. You got, or the diagram. You got V and W. V is n-dimensional, W is m-dimensional, right? And you're looking for a matrix that is an m by n matrix, right? The m by n matrix gives you some map, TA, that goes from Rn to Rm, right? By left multiplication of the matrix, right? And basically, what we're doing is that we're saying that we want we'd like some matrix A so that the behavior that it affects on the effect that it has on Rn, taking something from Rn to Rm, somehow parallels the behavior that T has from B to W. Okay, parallels in a very precise way. Okay, right. This right, because this thing V is isomorphic to Rn and W is isomorphic to Rm, right? Via the coordinate maps that we had earlier. Right? The coordinate maps we had earlier said that we have a map from V to Rn, which is an isomorphism. We also have a map from W to Rm that's an isomorphism, right? Using the basis map, using the basis. So let me draw it a little bit bigger here. So this picture again. Right. We have V, and for V we have some basis E. Okay. That gives us a map, right, from V to Rn. Right. The map that says take a vector here and map it down to its coordinate vector with respect to V. Right. This is the map that we were talking about at the beginning of class that you all said you understood. So I'm assuming that it's okay. W, we have the same thing. We have a basis F here, and that basis gives us this sort of map. It says takes W to its coordinate vector with respect to the F basis. Right? So we have these coordinate maps, okay? And they are isomorphic. Let's call this map P, and let's call this map Q. Okay, so P is this map, is the coordinate map, Q is this coordinate map. Okay. Now we have t here. Right. We have the map t, and what this A map is, right? What is A? What is this A? This matrix A? You notice what it says it does, right? It says that that if you take a vector and run it through T, and then run it through the coordinate map, right? Run it through the coordinate map. So if you take a vector, run it through T, and then run it through the coordinate map with respect to F, right? Then it's the same thing as if you took that vector and ran it through the coordinate map first, and then hit it with A. Okay. So A, right? A, right? So A is the matrix for which T sub A, the linear for which the linear transformation, the corresponding linear transformation T sub A makes the above diagram commute. Okay. And by commute, it means that if you go this way or if you go this way, you get the same thing. Okay. Okay. Everyone all right with that? Anyone have questions? It's a strange thing. It's a strange thing. It's your first contact with a commutative diagram, right? Yeah, Mia.
So would we find A by, is there an inverse to the coordinate with respect to B?
Yeah. So there is, exactly.
Okay.
Exactly. So these guys we call are isomorphisms. These guys are isomorphisms.
Are those, oh, I'm sorry, are those usually on their side?
Yes.
Okay, no, it's fine.
Yeah.
I thought it was letters.
Yeah, if I turn it sideways, then it would be written like this.
Okay,
Yeah.
okay, that's all.
Yeah, so P is this way. Q is this way. Right.
Okay.
T, A.
Okay.
If I turn it sideways, yeah. Okay. So, yeah. So, yeah. So, any questions about what this thing is? What A is? Okay. So A is going to be the matrix that makes this diagram commute. Okay. A is going to be the matrix that makes this diagram commute. And how do we figure out A? Yeah, Mia.
And T sub A is just left-hand multiplication of A?
Yes, by A. Yes, exactly. Yeah, I might, I could just as well write A here, but
Okay.
it's more precise to say. It's more precise to say we have this linear transformation here. Yeah. But the linear transformation is left multiplication by A.
Okay.
Okay. So how do we figure out A, right? So that's the big question, right? What is A? What is A? Right? How do you figure out A? And Mia has actually given sort of the answer. She said, is P invertible? Right? Does P have an inverse map? Right? P does have an inverse map. Right? This is an isomorphism. It's this map is the coordinate map, right? Taking a vector down to the coordinates corresponding to that vector. Okay. So the inverse map, P inverse, we do have an inverse map, P inverse, going the opposite direction. Namely, you start with some coordinates and then build the vector up here. So there isn't, these guys are isomorphisms, so there is an inverse map. So here's one way of expressing what we're going to do. I'll explain it in two different ways. Say, well, P is an isomorphism, right? So, and thus invertible. It's invertible. And so let's, sorry. Let me make one comment about this thing, okay, first. So Mark, notice that if I write this, it's the same thing as saying you take V and then run it through P first, right? And then hit it with T sub A. The left side, right? You take V and you hit it with P to get the coordinate vector with respect to E, right? And then you hit that thing with A. And then over here, what should I write on the right hand side? T, V, and then you take the coordinate vector of it. So what am I hitting it with? Don't blurt it out. What do I write here? Okay, blurt it. Anybody want to say?
I have a question.
Yes.
So PV is the coordinate vector.
Yeah.
Times, so it's like C1, B1 plus C2, B2.
It's the C's. It's the C's.
Times the vector. What is V?
Okay. So all I'm saying is that let me write this using the P's and Q's. Okay. Instead of writing it like this, I'm gonna write instead of writing V sub E, I'm gonna write P of V.
Okay.
Right. So you take V and then you hit it with P. Right. You take V and you hit it with P and you get this.
And V is
V is
vector.
yeah, any vector.
Okay.
Right.
And P is like C1, C2, C3.
P is the map that takes the vector and gives you the coordinate vector.
Oh, okay.
Okay. Okay. So remember at the beginning, it's sort of hard to keep everything straight in your head, but so you have a vector space, you have a basis, right? If you have a vector space and a basis, then you have this map from your vector space to Rn, right? That map is you start with your vector and you map it down to the coordinates. Okay, let's call that map P.
Okay.
Let's call that map P. Okay, so right. So instead of writing the vector's coordinates here, I'm going to write that as PV. Right, because PV is you take your vector and you map it down to its coordinates.
Mm-hmm.
Okay, so this literally is this.
Okay.
Okay, and then you take that thing and you hit it with A. Okay, so now I've written the left-hand side.
Mm-hmm.
Okay, now let's write the right-hand side. The right-hand side says take TV and then take the coordinates with respect to the F, right? So that says take TV, right? TV is over here, and then I want the coordinates with respect to F. That means
okay.
hit the thing with
Q.
Hit the thing with Q. Okay, so I'm writing the same thing. I'm just writing the same thing again here. Yeah.
So when you were saying T of A, is that like at the beginning of last class when you said they were the same as A?
Yeah. So it's probably more proper for me to write T sub A here. T sub A is the linear transformation given by left multiplication by A. Okay. So just keep that in mind. So we're trying to figure out what A is, right? You say, well, okay, P is an isomorphism, and so it's invertible, right? So let's consider QT P inverse. That's going to go from Rn. So it starts off in Rn, right? Remember how these things work, right? It's going to take somebody in Rn, right? Take somebody in Rn, and then go up through P inverse first, right? And then through T, and then down through Q, right? So it starts in Rn and ends up in Rm. Is this confusing? Right? P inverse goes from Rn back up to V, right? And then T goes from V to W. And then Q goes from W to Rn. Right? So this composition of linear transformations goes from Rn to Rm. Yeah, Haley.
So is that like with the dot thing from yesterday when you said S dot T, but it was backwards?
Yeah.
So like
So,
there's dots.
yeah, I had circles here for composition. But really, when one writes linear transformations, you just write the linear transformations. Yeah. Okay. So let's think about this thing. Let's look at this thing. Right. This thing goes from here all the way over. What's the this thing is a map from Rn to Rm, right? Well, being a map from Rn to Rm, it has a matrix representation, right? This has a matrix representation, right? It's a linear transformation between the Euclidean spaces. And so has a matrix representation. Okay. So what's the matrix representation? How do you find a matrix representation of something from Rn, from one Euclidean space to another?
Is it T sub A?
It will be T sub A, yeah. But what's A? What's A? How do we figure out what A is?
Do you use that? The thing in the box.
Think back to what we did right before this, which was, do you remember what we did? We were looking at, right before this, we looked at matrix representations of linear transformations between Euclidean spaces, right? How did we find the matrix representation for some map between Euclidean spaces? Ellen?
You ran the bases through the linear transformation.
Right. So we looked at, remember, we looked at the behavior on the standard basis, right? And then we used those guys as the columns of our new matrix. Do you remember this? Right, we did this last time, right? So it has a matrix representation, and the matrix representation will be, namely, A1, A2, it'll be like this, where AI is QTP inverse EI. So that sort of tells us what the matrix representation is what A is going to look like. What's P inverse of EI? What's P inverse of EI? Is the okay. Actually, let me. So I think maybe I should have done the second explanation before the first explanation. So I'm going to hold this for a second. I'm going to explain it in a completely different way, and then I'll come back to this. Okay. Yeah, Haley.
For the E, that's for this basis, not standard basis, right?
For this, no, this is the standard basis. This is still the
Is that
standard basis.
this used too?
No, no.
Okay.
Yeah, that's not the standard basis.
So, because don't we use standard basis for Euclidean spaces?
Mm-hmm.
Are we doing this in Euclidean space? Or?
Yeah, actually we are.
Oh.
We actually are going from Rn to Rn.
Oh, so we're not in vector spaces.
Right.
Okay.
Okay. Let me sort of start over here. I think it looks like I feel great. I'm not sure if I'm right here, but I feel like there's a great cloud of confusion. Is there a great cloud of confusion? Close your eyes for a second. Raise your hand. Raise your finger if you're like completely lost. Okay. Not so bad. Okay. Open your eyes, please. Okay. Yes, Mia. Okay. And now I'm gonna keep on going. Actually. Yeah.
Is P inverse E sub I P? Is it like the? Never mind, I lost it.
Okay.
Is it a column vector?
E sub I is a column vector, right? So like E1 is 1, 0, 0, 0, 0, 0, right?
Mhm. So P inverse of, or left hand multiplied times E1 would be a column vector.
Well, no. Okay, I'll let you guys think about it. Take 1 minute and see if you can figure out what P inverse of E1 is. That'll show if you actually understand what we're doing.
And then we do that transformation from V to zeros. My guess is that then a constant or like a single entry.
So if we have like E times possibly, if we have like A times ones, this was
Amelia.
Is it V of
Very good. You get it also? Hello? Right. V1. I hope that's right. Yes. Right?
or VI?
If it's EI, then it goes to VI, right? Does everyone? So, right? Remember what P is, right? P goes from vector to coordinates, right? From vector to coordinates based on the E basis, right? The E basis was V1 through Vn. So it says, take your vector, express it in terms of these guys, and then map it down to the coordinates, right? Now, P inverse is going to do the reverse, right? It'll say, here are you give me these coordinates, I'm going to reconstruct something up here based on those coordinates, right? So if you give me 1, 0, 0, 0, 0, 0, I'm going to take 1 of the first guy and 0 of the other guys, right? So P inverse EI is going to be VI, right? P inverse V1, P inverse E1 is V1, P inverse V2 is E2 is V2, etc., etc. Right? P inverse VEI is VI. questions? Ask questions if it's confusing. Charlie, you okay? Okay. Chelsea, you okay? Okay. Anyone? Charlie? Okay. Quiet ones. I'm gonna ask all the quiet people. Andrew? You good? Good. Okay, good. I have no sense of you guys. You look confused. You look confused, but it's simply because I think you're confused. It's simply that I think you're confused. Okay, right? Okay, so what is the matrix gonna be that makes this what is the matrix gonna be? Well, it's gonna be TVI, and then you run this thing through Q, right? So Q, remember what Q does? Q says take the coordinate vector with respect to f. Right? That's what Q is. Q is the thing that says take your vector and then express it, give the coordinates with respect to f. Okay. Right? So that actually is the matrix that makes this thing work is actually the one where you take the basis vectors of E, you run them through T, and you express them with respect to f, with respect to the second basis, and that's going to be your matrix representation. Okay, I'll make this more concrete in a second. Okay, right now, so that's explanation 1. Okay, or maybe that should have been explanation 2. Let me give you explanation 1 now. Okay, so right, what A works, right? That is what A makes A VE equal to TVF for all V and V. Okay, and so here's what we're going to guess. We're going to say, well, take A to be some matrix A1 through AN, where AI is TVIF. It's TVIF. In other words, you take the basis that you're given for V, you run each one through T, and you express each one with respect to the second basis, the basis of V, of W, and you make a matrix out of those guys. Okay. Okay. So I claim that this is the one that works. So I claim that A VE equals TVF for all V and V. Okay. I claim that this is going to be the one that works. Okay. Why? Right. Why? Well, if I look at QTVI, right, and again, let me write this as, we're trying to show that TAPV equals QTV. Okay, so I claim that TAPV equals QTV, or QDV. I.e. that TAPV. So this is what we're trying to show, right? That this matrix makes this happen. Okay? If this happens, we're great. Okay? So you say, okay, well, if I look at QTVI, of course, that's TVI with respect to the F basis, just by definition. Right? And TAPVI equals what? This is the same trick question. TAPVI equals what? Think for 30 seconds. Haley? TVIF, exactly, right? Right, because PVI is what? Did anyone see the joke? This is sort of humorous. PVI, well, that says take VI and take its coordinates with respect to the VI basis. What is VI's coordinates with respect to the E basis? What are its coordinates? How do you express VI? How do you express V1 using the VI's? Well, it'll be 1 V1 plus 0 V2 plus 0 blah, blah, blah. What's the coordinates of V1? E1. Right? What's the coordinates of VI? EI. Right? So this becomes TAEI. Right? What's TAEI? What's TAEI? Well, that's, of course, AEI, right? You know, it's the AI. Right? In other words, AI, which we constructed as TVIF. Right? So what does that tell you? That these two linear transformations agree on the E basis, and as such, they agree everywhere. Because of that, they agree everywhere, right? Because you've got these two linear transformations, and they agree on a basis. Right? So hold on, Teresa. So thus, QT and TAP agree on E, and so QT equals TAP, right? In other words, you know, QTV equals TAP, TAPV for all V and V. So the matrix you need to make the diagram commute is exactly the one you get if you take the basis that you're given here, map each one through T, and then take the coordinate vector, and then put all those guys as the columns of a new matrix. Okay, and that will be the matrix that represents your linear transformation. Yeah, Teresa.
When you're writing PV, is it P times, like not sub V? It's because you write TA, sometimes they get
T sub A, but
T sub A, but P times V.
P times V,
Okay.
yeah.
You wouldn't denote P with like a sub.
No,
It's
no,
not
no.
trans.
No. So this is really, you know, I mean, it's P applied to V. If you want, you can think of it like this: P of V,
Okay.
right? P takes in V like a function takes in V. And people usually leave, for linear transformations, people usually leave these things off. But if you want to think of it like a function, I mean, it is like a function, right? It takes in a vector, right? It takes in a vector and then takes in a vector in V and then gives you a vector in Rn, right? Okay. So that's it. This is how you get the matrix representation. Let me try to make this concrete for you guys. Okay. So suppose that V is P3 and W is P2. Okay. polynomials of degree less than 3, polynomials of degree less than 2, right? And T is differentiation. Right? So T goes from V to W. Right? And we're trying to find a matrix that acts like differentiation. Right? We want to find a matrix that represents the behavior of differentiation. Okay? And somebody gives you some sort of obvious bases. 1x squared is your first basis. And your second basis is 1x. Right? These are sort of the standard bases for P3 and P2, of course. Okay? So here's, right, V is three-dimensional, right? You have this nice basis here. So you have a map to the coordinates, right? Right? The coordinates are going to be in R3, here the coordinates are going to be in R2, right? Okay. Okay. So we're looking for the map, the matrix A, like the 2x3 matrix A, that gives us something that completes this thing here. Okay. We say, okay, well, A we saw is going to be A1, A2, A3. So A is given. A we saw is given by AI is PBI with respect to the F basis. Okay, so let's work those things out, right? You take T of the first guy and express it, right? So what's T of 1? What does T do to 1? 0, right? T of the second guy, right, is 1. T of the third guy is 2x, of course, right? So you take those guys, right, and express them with respect to the F basis, right? Well, with respect to the F basis, what do I write here? I've got 0, and I'm going to express it with its coordinates with respect to these guys. Well, 0 is going to be 0 the first guy plus 0 the second guy. Right? I get 0 is 0 here. Right? Tx with respect to the F basis is 1 represented with respect to that, the coordinates of 1 with respect to that F basis. Right? So what do I write here? Haley? 1, 1?
0.
1, 0. Yeah, 1, 0. Right? Because 1 is 1 of the first guy and none of the second guy. Right? And then Tx squared, right? F is going to be what?
0, 2.
0, 2. Okay. And so our theory says take A to be this matrix 0, 0, 1, 0, 0, 2. And this thing should behave like the like differentiation does. This is differentiation right here. This matrix. Okay, you didn't recognize it, right? Nobody taught it to you like this, but this is differentiation for high schoolers, maybe. Okay, right? And you think, okay, well, in what sense is this differentiation? Well, you say, well, look, if I took, say, 3x plus 4x squared, okay, and I differentiated it, right? Of course, I get 3 plus 8x, right? Oh yes.
For the second one,
Yeah.
for Tx, shouldn't it be 0, 1 because it's 0 times 1 and then 1 times x? And that's how you write x in terms of f?
Tx is 1, right? Tx is 1.
Oh, yeah.
Yeah.
Yeah, sorry.
Okay. Okay. So suppose I let's see that this thing actually does behave as we want it to, right? Suppose I start off with 3x plus 4x squared, right? And I run it through I differentiate it. Well, I end up with 3 plus 8x, right? Okay. Now let's see how this matrix does exactly the same thing. You say, well, look, if I start with 3x plus 4x squared, and I map it down to its coordinate vector, right? Its coordinate vector is going to be, remember, we've got 1x squared here, right? The coordinate vector is 0, 3, 4. right? 0, 3, 4, right? That's the coordinate vector. If I take this guy and map it through, right? 3x plus 4x squared, right? With respect to the e basis, it's going to be 0, 3, 4, right? And I hit that thing with a, 0, 1, 0, 0, 0, 2, right? And what do I get? Well, I get 0, 3 plus 0, so I get 3 here, and I get 8 here. I get 8. I get 3, 8, right? And you notice that 3, 8. So, right. So I run the thing through the matrix. I hit the thing with the matrix, and this thing gets mapped over here to 3, 8. And lo and behold, that's the same thing you get if you come down. Right? If I start with hit this thing, differentiate it, and then go down to its coordinate vector, it's the same thing as if I go down to the coordinate vectors first and then map it through the matrix. Hit it, left multiply it by the matrix. I get the same thing. It's not a miracle, right? We showed that this is going to happen. We are guaranteed to happen. Okay, so this is differentiation, right? At least for in this simple setting, and that's why you can teach differentiation in high school, right? Because people just memorize the power rule. This is basically like the power rule right here. Okay, the power rule is so simple that you can embody it in a matrix. Of course, actual differentiation is not so easy. Okay, everybody see that? Right? This is what we mean by matrix representation. Okay. Yeah, I guess that's it. Okay, we'll talk. We still haven't finished.